So let us repeat what you theoretically learned from this last section. And the best part is that you can always go back to any of the videos and listen to them in your own rhythm. So you use the Rhino wizard to create your first plugin, an actual plugin that works, your own command that executes inside Rhino, and we talked about some basic structure of your plugin, what different files mean. And do not worry if you do not remember that now. The files that are important will come up again and again, and you will learn how to use them. I showed you how to use Rhino Common SDK help and how to create a toolbar with your commands if you want to be organized. Personally, I like to write commands. I like that coder feeling instead of clicking on images, but we are all different and you can find your own ways of spell casting. Maybe menu is your preference. And let's go into deeper waters now and start with a simple example of selecting a point, which will introduce new challenges for us. We will start with an example and then back up a little bit and explain how selecting reading geometry actually works, and we can stay in our own command for now. And let us do it very slowly, explaining every line. So just go to our command and simply delete everything aside from the returning of the success. And in order to pick a point, we will use the class getPoint, designed especially for that. So we can simply write var gp equals getPoint. I don't know at this point if I actually mentioned what this var means. It's a way of .NET recognizing automatically what this function, what this method returns. It's a generic variable so that you don't have to explicitly define it. I talk a bit more in the C# basics lessons, and if you don't understand what it is, just simply Google it. It's very simple. I'm not going to explain it at this moment. So as we can see, this getPoint class is not recognized. We learned how to solve that problem. We will try to find a getPoint class. We will get different methods here. It's just, you can simply press on any method and you can see you will see it get its class at the top. And you can see that the getPoint class belongs to the namespace called Rhino Input Custom, and that's obviously what is missing here. So we will add that. So now let's step back and see what we created here. We created a new object of a class getPoint and we called it GP. So we learned that you can make an object of a class, or to use a technical term, instantiate a class using the new keyword. Now in C++, for example, you have to explicitly define your variables. You have to match this exactly to this method or this class. So in C++, we would actually write getPoint, so to explicitly define it. But in C# you have something that's called an implicitly defined variable or implicitly typed variable. You can simply write var generically, and the compiler will actually infer the type of the variable being declared. If you're very fastidious and accurate, you might want to use strongly typed variables. I often do, as my experience from C++ taught me. But if you do not want to concern yourself much with the types, just write var, and the compiler will automatically recognize the type of this object for you. After we used the namespace and declared this, we can access its variables and functions. And we do that using the dot operator. Once you do that, you write gp dot. Visual Studio IntelliSense will show all the functions and variables you can access. You can see the same list in your help file, as I've shown you before. In the getPoint class, the getPoint methods and properties are all listed here. So that is what you can see here when you type a dot. And you can additionally see the methods that you can use from all the parent classes. One of the standard functions is setCommandPrompt. And that is what we will use. And since this function needs an argument and a parameter, and the parameter is some type of text or string, as we can see. Here is the parameter. You can see that in the help file as well. A string is one of the standard classes for writing text. Then we need to provide one. So let's just simply write pick a point. You can do this, or we can try to learn as much as possible here, and we can make an object and then give it a value. So we can make an object called prompt, let's say, and we can initialize that object with some text. And then we can actually pass this here. It's the same thing, only a bit longer, but sometimes useful, as you will see. Now we will actually call the function that prompts the user to pick the point. And in the case of getPoint class, that method is called simply get. Now at this moment, our object GP of type getPoint will know if the selection was successful or not, right after this method. There's a method of the class point called commandResult that will return the type result. So if you actually write this, just to make it more clear, type result is command result. So this method will tell us how successful this was, and we will save it in this enumeration. Now let's remember what values res can have. Now what you want to do is simply go to the help file, and you need to find the result enumeration. Let me see if I just simply write result, if I'll get something. I'll probably get a lot of things that I don't need, but I know exactly where to find it. In Rhino commands, I will find my result enumeration. And if the user pressed escape, for example, or cancel the command, we do not want to continue executing. So there are different ways a command can be unsuccessful, but we only want to continue if it was successful. So what we can do is we can write if the result is not equal, this is the not equal operator that I talk about in my basic course, the result enumeration and its success version, then we will simply get out of the functions right away by returning the command result, whatever it is. It doesn't matter at this point. If the result is a success, our function will just continue to execute here. So if you use return, you stop the execution of the function, but you can learn about that, the if statement and the logical operators, as I said in my C# basic videos. So I hope this is not too slow for you, because I'm trying really to explain all the basics. Okay, so we saw if it was successful, and if it was, we can simply extract the point. The point is saved in our GP object. So we will again use the var for our point, and we will call the point method of our getPoint class, which will return the selected point. Now in this exercise we will simply write the coordinates of the point, and this is how we will do it. We will just create a variable to hold the text of the coordinate x. Then we will access the x coordinate. So we can do it like this: variable x. We access the point x coordinate, and I'm doing this very slowly, step by step, so you can understand how classes and methods work. Our variable point saved the result from the method point, but since we wrote var, we are not sure what type of object we saved there actually. Let's find the point method and see what it returns. So we had our getPoint class somewhere back. Yes, getPoint class, and in its methods we will find our point function, and we will see that this function returns a point 3D, the one that we actually were familiar with before. Now let's find point 3D, or simply click here, and we see what properties it has. It actually has x, y, z coordinate properties that we can access. So that is exactly what we need. We will simply write dot access this property x, and then x is a double precision number. It is a variable that holds a double precision number. So check what double means in more detail online or in my C# basics video if you do not understand. And in the help file you can see again at the point 3 structure, you can see that x, if you press on it, that it's a double number. Again, I'm aware I'm doing this very slowly, but don't worry, I will speed up as we go along. So the only problem is we want to write a number in our command prompt, and we need a string for that and not a double. Well, in C# you can always use a very useful toString function, that's all numbers have, to convert the number to the string. Let's do this for all three coordinates. You can simply copy and paste this. We'll have our y and z, and here y and z coordinate. So now we will want to write all these coordinates in a simple line, and we will use the Rhino app write line as we used before, and I will explain it more detailed in the next video. But in order to use this, I would like to format in the way I write this a bit more neatly. And this is what I will do. You can take this for granted right now, but I will explain later how this is used, I think already in the next video. So I will define the simple variable called format, and then I will use a static method of the class string, of the type string, and here I'm basically defining how I want to write these variables, and I will write something like this that you can, as I said, take for granted for now. And I'm just saying that whatever I put as a variable inside my string, it will have a certain display precision, and this display precision I will retrieve from my document, from whatever is set in my settings. So now I want to put this before so that I can actually pass this format to the toString function. And now this double precision coordinates will be written with a precision that's defined in our project, and we will see how that looks right away. We will use Rhino app write line, and I told you I will explain this more in the next video, but we can simply write world coordinates, and then we can put our variables in brackets. 0 will be our first variable, 1 will be our second variable, 2 will be our third variable, and at the end we will simply address them. Let's build this and test this. We already have our plugin with this command installed, so if I pick a point, you will see world coordinates 2.04, 10.85 and 0. So I can execute it again, press anywhere, and I will see the coordinates of the point I pressed. But for now, notice that the getPoint class is actually derived from getBase class, and getBase class has a lot of interesting methods. You will see you will be able to set a geometry filter to define if you want to pre-select objects or not, but we will see that in our following videos. And before we continue selecting and reading geometry, let us address this writing in the command prompt, as it will be very useful for you. Very often you will want to write something in your command prompt. You will sometimes want to keep track of the iterations in your application, but we will cover that later. More often you will just want to write something like command executed successfully, or you selected 25 surfaces, or error the code stopped inside function X. There's a very simple way to do this. We will access the Rhino app class and use its write line method. The cool thing about this is the number of ways you can format the string variable. And let's see how to do that by expanding our command a bit. I just wanted to use a very short video to kind of explain what this write line is. I mean, it's kind of obvious already what it is. It's just print something in your command prompt, but I wanted to dedicate a short video to it because you will use it a lot for your own debugging techniques. All the time you can put this in your methods, in your functions, just to print out something to see where you are at the moment and if you have what you need. What I did here is simply add something that you can add when you want to add a new line. If you want to skip a couple of lines or skip one line, you can call the environment and its new line method. This will just simply add a new line to your string. This formatting I explained shortly. This is how you can format different strings and actually pass it. Here I will not go into detailed explanation of how this works. You can check it out online because I don't want to go into explaining now how the string type works, because it's out of the scope of Rhino programming, I would say. But the interesting thing I find is the fact that we are accessing the document and we are accessing a thing that's set in the options. So you have to remember that everything that you set in your Rhino when it comes to options, tolerance, unit tolerance, angle tolerance, whatever. You can access it here from your Rhino document and read it out. And this is what we did here for the display precision. There is another interesting thing that you can also explore on your own if you want. And this interesting thing you can find following this link. And it will point out to you that depending on the user's culture settings, their computer may be set up to use commas instead of period and decimal separation and stuff like that. So you might actually access something that's called culture info that I will not elaborate on, just show you how it works on an example. You can define your variable. Let's call it provider. And then you can use this system globalization, namespace culture info, and call its invariant culture, which will get the object that is culture independent or invariant. And afterwards, you can find it useful. For example, imagine if you want to write a percentage number. You can do that. You can simply define some number. Let's say it's 56. And if you want to write this number as a percentage, what you can do is write line and then call number to string. And as we already learned, you can format this string by passing some arguments, and you can pass this. In this example, you can pass p1 and just use the override of this, the overload of this toString function, where you can also pass your provider. What you want to use usually is a number between 0 and 1, so that you can actually get 10% in this case. What you can use instead of P1 is you can use F1, F2, and that will actually define the number of decimal places. So we did this a little more complicated because we wanted to access the document, but if you wrote simply here F1 or F2, that would also limit and show you this number with this number of decimal places. If you have a write line that's very long, and you want to break it into multiple lines, you can do it. And now if you press enter, Visual Studio will kind of take care of it, and you will see that it will add a plus here. So you don't have to think about it at all. What you can see is what it did is basically close the quotation marks, gave it a plus number, and then continue it here. You don't want to press enter without closing the quotation marks, so that's a small tip. Of course, there is no sense in me going through the hundreds of variations of formatting a string. The most important thing is that you can understand that you can format a string, and that you can find all the explanations online, like in the links I posted. And you will see in the following videos and in our examples which methods we will use 99% of the time. When you write plugins for Rhino, your actions will usually involve selecting the geometry that already exists, creating the geometry, and in 99% of the cases, your plugin will do a combination of both. In this section, we are concentrating on selecting or reading the geometrical objects that you have in your document, and in more technical terms, this is the geometry that is already written in the Rhino document. When I draw a single curve or load some Rhino file, different objects will be loaded into your memory. By accessing those objects, you will be able to copy them, transform them, use them to create new geometry, etc. If you do not understand yet what a class is and what basic inheritance is, maybe you should pause here and watch or re-watch my C# Basics course videos that deal with that. If you already know, then you should know that the base class for geometrical objects in your Rhino document is called a Rhino object. Quite logical, no? So if you simply go to your Rhino SDK help file and check it out, and again, as I said, if the whole link doesn't work, you can use this shorter link and then simply click on Rhino Common. And if you find your Rhino object, let's find it. Rhino object, here is one method that belongs to Rhino object, and at the top we can find the class immediately. It says exactly that, represents an object in the document, and should only ever be creatable by the Rhino document. There is another class you should get to know, and that is objref, so object reference. Let us see what Rhino SDK help file tells us about that. I found the constructor. You always have to get a bit creative with this. If you're searching like this, you can click on any method or constructor or whatever, and then you will see the class on the top. It says that it represents a reference to a Rhino object. And this is how it works. We're not going to create any new command or anything. We're not going to execute what I'm writing now. I'm just writing it inside the Visual Studio so you can see the code. We will use this later on. We have to see the namespace it belongs to. First of all, it belongs to the Rhino document objects. And let's write this down in Visual Studio. I will write it right here in the command. I will not execute this code. I'm just using Visual Studio to show you how you can select an object with a single line, basically using the object reference. So I added the Rhino doc objects because we will need that namespace to access the object reference class. We will define our object. I will need now the Rhino get, and you will see in a moment why. And if I go to my help file, I see that the Rhino get class belongs to the namespace Rhino input. So I will add that as well. And I will simply save the result enumeration in this variable res, and I will call my Rhino get class. I will call its method called get one object, and then I will pass some things. I will pass the prompt, select something, let's say select curve. As I said, you will see in more detail how to select different objects. I'm just trying to point out the importance of object reference. Select curve, let's say. Then what you need to do is to pass a boolean that allows the user to press enter. We are not going to allow the user to press enter. We want him to select the curve. Then we can immediately set the geometry filter. As you see, we're using the object type enumeration here. And the most important thing, we are going to get our object reference back. This is how we can select an object. I don't need this. I don't know why I wrote it. Sorry for that, if that confused you. But here we already have res here, so let's rename it just for a second. Okay, what you see now is that you have an out keyword. You can check this online or in my classes, but it simply means that we are passing this variable by reference, not by value. That means that this variable can change inside the function, and in this case it will. The value will reference the object that the user selects, and afterwards you will be able to access that object using the reference. For example, like this, I will assume that the user select a curve object. I will use the class curve to save it, and I will simply access the object reference and its method. I'm full of spelling mistakes today, and am I not? Object reference, object reference, object reference. And I will access its method curve. Then I can check if my curve is 0. I can return failure like this, and if it's not, I can continue. There are many ways to select objects. That's why I showed you this one that we will rarely use, but it is a legitimate one. And the fact that there are many ways should not be intimidating to you. It should make you relax, because you can get creative and do things your own way. And I wanted to show that an object reference class can be used very well for this type of cases. And Rhino object and object reference, or objref, are powerful classes, and for our purposes, especially in the level 1, we will only use a small portion of their members and methods. But in the following videos, you will see that whenever we read an object from a document, we will be accessing it over these classes, and that whenever we draw something in the document, we will be adding a Rhino object to it. Now, before we see it, we will make one more short stop and explain what geometrical types we will be dealing with. When you write plugins for Rhino, your actions will usually involve selecting the geometry that already exists, creating the geometry, and in 99% of the cases, your plugin will do a combination of both. In this section, we are concentrating on selecting or reading the geometrical objects that you have in your document. And in more technical terms, this is the geometry that is already written in the Rhino document. When I draw a single curve or load some Rhino file, different objects will be loaded into your memory. By accessing those objects, you will be able to copy them, transform them, use them to create new geometry, etc. If you do not understand yet what a class is and what basic inheritance is, maybe you should pause here and watch or rewatch my C# Basics course videos that deal with that. If you already know, then you should know that the base class for geometrical objects in your Rhino document is called a Rhino object. Quite logical, no? So if you simply go to your Rhino SDK help file and check it out, and again, as I said, if the whole link doesn't work, you can use this shorter link and then simply simply click on Rhino Common. And if you find your Rhino object, let's find it. Rhino object, here is one method that belongs to Rhino object, and at the top we can find the class immediately. It says exactly that, represents an object in the document and should only ever be creatable by the Rhino document. There is another class you should get to know, and that is objref, so object reference. Let us see what Rhino SDK help file tells us about that. I found the constructor. You always have to get a bit creative with this. If you're searching like this, you can click on any method or constructor or whatever, and then you will see the class on the top. It says that it represents a reference to a Rhino object. And this is how it works. We're not going to create any new command or anything. We're not going to execute what I'm writing now. I'm just writing it inside the Visual Studio so you can see the code. We will use this later on. We have to see the namespace it belongs to. First of all, it belongs to the Rhino document objects. And let's write this down in Visual Studio. I will write it right here in the command. I will not execute this code. I'm just using Visual Studio to show you how you can select an object with a single line, basically using the object reference. So I added the Rhino doc objects because we will need that namespace to access the object reference class. We will define our object. I will need now the Rhino get, and you will see in a moment why. And if I go to my help file, I see that the Rhino get class belongs to the namespace Rhino input. So I will add that as well. And I will simply save the result enumeration in this variable res, and I will call my Rhino get class. I will call its method called get one object, and then I will pass some things. I will pass the prompt, select something, let's say select curve. As I said, you will see in more detail how to select different objects. I'm just trying to point out the importance of object reference. Select curve, let's say. Then what you need to do is to pass a boolean that allows the user to press enter. We're not going to allow the user to press enter. We want him to select the curve. Then we can immediately set the geometry filter. As you see, we're using the object type enumeration here. And the most important thing, we are going to get our object reference back. This is how we can select an object. I don't need this. I don't know why I wrote it. Sorry for that, if that confused you. But here we already have res here, so let's rename it just for a second. Okay, what you see now is that you have an out keyword. You can check this online or in my classes, but it simply means that we are passing this variable by reference, not by value. That means that this variable can change inside the function, and in this case it will. The value will reference the object that the user selects, and afterwards you will be able to access that object using the reference. For example, like this, I will assume that the user select a curve object. I will use the class curve to save it, and I will simply access the object reference and its method I'm full of spelling mistakes today, and am I not? Object reference, object reference, object reference. And I will access its method curve. Then I can check if my curve is 0. I can return failure like this, and if it's not, I can continue. There are many ways to select objects. That's why I showed you this one that we will rarely use, but it is a legitimate one. And the fact that there are many ways should not be intimidating to you. It should make you relax, because you can get creative and do things your own way. And I wanted to show that an object reference class can be used very well for this type of cases. And Rhino object and object reference, or OBJRef, are powerful classes, and for our purposes, especially in the level 1, we will only use a small portion of their members and methods. But in the following videos you will see that whenever we read an object from a document, we will be accessing it over these classes, and that whenever we draw something in the document, we will be adding a Rhino object to it. Now, before we see it, we will make one more short stop and explain what geometrical types we will be dealing with. There are many types of objects in Rhino. There are, for example, different annotations like text dots, text, dimensions, etc. They have their own classes and ways of selection. Some of them we will cover later, and some of them in more advanced level courses. But now we will talk about basic geometry types, namely points, curves, breps and meshes, and we will learn how to select them and read some basic information. See this video as a theoretical introduction into different geometry types, and later you will learn how to use different classes that represent them in your programming. A point is the simplest geometrical object, and in Rhino there are several variables that can hold the point information. For example, structures like point 2D, point 3D, point 3F, and so on. If you go to the Rhino geometry namespace, you can see them. Most of the time we will use the point 3D structure to save points, and I will tell you when there is a need to use some other type. For an array of points we will have different types of lists, but it is good to notice that in the Rhino collections namespace there is a class called point 3D list that can be used for storing a list of points. As far as the curves go, as you probably already know, Rhino works with NURBS geometry. If you do not know what that is, you can look it up online or check out the links for some of my videos. If at this point I made a course on NURBS geometry, then you will find a link for that as well, because I plan to do that. So Rhino will have free-form NURBS curves with control points, knots, directions, etc. You will be able to select them and read all that data from them, and also create them automatically. The mother class for curve is, well, curve. This is the base class, and there are many other classes that can be used to hold curve-like geometry, from the simple ones like line structure. Then you have line curve over arc structure, arc curve class that can hold arcs and circles. Polyline curve can describe polylines, polycurve that can represent joint curves. A NURBS curve, for example, can be used to create complex NURBS curves. You can find all these types in the Rhino geometry namespace. You will notice that there are often simple versions like line structure that just has the start and end point and nothing more basically, and line curve that is a NURBS representation of a simple line, and it's inherited from the curve class, which is in turn inherited from the geometry base that provides some common methods and properties for most geometric classes. With most curve types you will have some basic structure and a NURBS form, and in practice you will decide which one is better for you to use. The classes inherited from curve will have more flexibility and methods attached to them, but if you do not need all that extra load, you can stay lightweight and use the simpler versions. But we can deal with that once we actually use them, because an abstract explanation will not do you any good. All surfaces and polysurfaces in Rhino you will get to know as breps, a short term for boundary representation. The class that you will use most of the time will be Brep, and there are classes like surface, for example, but as you will see, especially at the beginning, Brep will be the main one. In Rhino you can model simple surface, but then you might want to connect 2 or 3 of them together. Then you might want to trim them, you might want to pierce some holes, close them, etc., etc. So what you need is a single class, a single object that holds all that information, all those surfaces and vertices and trim lines, That is a Brep, a very powerful representation that will hold all that information and enable you to do complex geometrical operations with some surfaces or polysurfaces, trimmed or non-trimmed, joined or exploded, and you will see how that works. I suggest you check out this video where I explain the basic differences between NURBS and mesh geometry. The link will be in the description as well. Let's just say that the mesh is the simplest and most ubiquitous way of representing 3D geometry. Meshes only have information about vertices or points in space and faces that can be triangular or quadrangular usually. Every triangle or quadrangle is just an array of 3 or 4 members representing the vertices that define them. That is all. 1,000 times simpler than a mathematically precise NURBS representation, and at the same time much lighter in programming terms, but at the same time much rougher and not so precise. Mesh is very different from NURBS, and you just have to be aware of that and know when to use one and when another, and when to transform one into the other. The class that can be used to hold the information about the mesh is mesh, and we will see how to use that variable to store a selected mesh and how to use it to create a mesh from scratch. So let's start selecting objects and reading their information. Now that we have learned about some basic geometry types, let us start with a point, and more precisely, let's see how you can select or pick a point and how you can save its information, read it, and use it. Actually, we already learned how to pick a point in our command in the first video, but there is a difference between picking a point and selecting one. If you want to draw a line in Rhino, you are picking points in space. You do not have to have points that are actually drawn, but if you want to create a curve through points, you have to select points that already exist in the document. With that distinction in mind, let us make a new command. We already learned how to do this. We can press right click on our commands. We can add a new item. We're interested in empty Rhino command. You can filter it here if you want. And since the goal in our lessons is this lesson is to pick points, let's call it X point picker. Again, I'm putting X so that later in Rhino we can start our command with X and see all our commands, because I don't think there are any Rhino ones that start with an X. So it's easier to filter through them. We can edit, and as you see, we have a new file in our commands and we have an empty command. What we want to do is pick points, and we already learned how to pick a single point here in our Variagola command. So we can actually start there. We can just copy paste what we need and expand the example to pick multiple points. So let's just copy this part here to our new command. Remind ourselves quickly. We created the object getPoint. Of course, we will need to include some namespaces. We will do that one by one based on what we need. We created the getPoint object, we set a command prompt, and we want the user to get it. If you do not know anything about loops, like how to use standard for loops, while loops, do while loops, I would suggest that you Google that shortly or watch the video in my C# basic classes where I explain that. It's pretty intuitive, so if you're a fast learner, you can just continue to follow the lesson, because we are about to use a while loop. We are going to wrap this point selection of ours in a while loop by writing while true. So we are always passing true. We're kind of entering an infinite loop. Let's put the curly brackets on and move all this code inside. We will change it. And outside the loop, we will create an array of points where we will want to save the information about all the points that we created. So, an array of points is something you can find also in your help file. It's called point3dlists points. And as you see, of course, we cannot find it yet. The reason is that we don't have all the namespaces included, and I said we will include them one by one to see which one is for what. For the list, we will probably need collections. And yes, now we have our point array recognized. And of course, we will have to initialize it like with any class. And we have a new array. Now this is just one way to write an array. You will see later we will use lists We will use Rhino list and different ways to write an array, but it's the same thing more or less, and in this example I will use this one, and I will talk about arrays at the end of this section. I find it simpler if we just use this point3d class now. If you have no idea what an array is, it's just a list of objects of different types, a group of objects. And as far as the notation goes and the operation we will use, now they're pretty intuitive, but if something confuses you, don't worry, I will explain them as I said more extensively at the end of this section. And now when we enter an infinite loop, we can create an object of the getPoint class, what we already did, ask the user to pick the point, and now let's optimize this a bit more. Now we can save the result and we can define it simply like this, implicitly. And now let's throw in some checks to see if we should continue looping or get out of the array. So if you check the while and for loops, do you remember how do you get out of one? Well, I will remind you in a moment. If we use the get function of the getPoint class, the get function returns a pretty cool type. You can check it in your help file. I will not do this for you this time. You can go to your help file and check the get result enumeration. We will check it probably in the future as well. But you can see that we will not only know if the user pressed escape or not, or entered a number, we will know which type of geometry he selected. Okay, I'll check it out with you. Here you can see I found in my Rhino input, I found the get result enumeration. And we will not only know if the user pressed enter or escape or entered a number, we will actually know which type of geometry they selected, if they did select us one. So let's check it out. We will need the Rhino input namespace in order to use this type of result. We got Rhino input custom, but what we want is a Rhino input as well. And if the result is a point, let's say it like this. If our result is a get result point, then we can do something. What can we do? Well, let us access our Rhino document, let us access its objects table, and let's add a point. We can access our GP object and its point method that will return what we need, a single point. We can access the views of our document in order to redraw them, and we can add the point to our points array. You can simply use the add function and again access the GP point. Now if you're wondering why do we have these double equal signs here, go fast and Google the if statement or check the video in my C# basics that explains how to use them. And if you know how, let's continue. It's very important that you do not make this mistake of putting just only one equal sign, but I talk about it in my basics videos. If the user presses enter, for example, or something like that, we can read that as nothing, as the explanation in the get result will tell you. Here, user pressed enter, they selected nothing. So we can check that. We can check what happens. The result is nothing. We will recognize that and do something. So what we will want to do is simply get out of the loop. And how? Yes, you're right, with the keyword break. That is how we get out of the loop. We will jump out and we will return success here. You know what? Let's save this return variable so we can have more control over it. This return variable is of type result, as we have learned, and we can say command result is here, uninitialized here. We will return it, and everything went well. We can set it to success, and in this case, when the user selected nothing, we can just set it to failure, and then this command will simply return failure. And if the user cancelled, escaped from the command, or did anything else, we can again get out of the loop and can return the command as a failure. So let's say In any other case, result, and we can actually return a result cancel. That's also an option, and break out of the loop. Now at this moment the cancel and the success of the command make no difference, but they will later, I promise. So let's do something with the array now. Let us, for example, print out how many points the user actually drew. So we can use our write line and say, I'm sorry about the L, it's a habit from the C++ where you actually have to write the L in front of the quotation marks. The user drew, we can use our curly brackets with 0 points successfully. And now we can access our points array and its method that's called count, that will give us the number of in the array, and because we want to write it in the line, we will simply cast it to a string. And that's it. Now let's build this command and see if it works. What I would recommend to you as an exercise, you could write a line here and another line here. One here could say, for example, the user pressed enter, so you can see that you can recognize these different actions. So we will go to our plugin manager, because we added a command. We will need to reinstall our plugin again. And now our command is called a point picker, right? There it is. Now we pick a point and we are in a loop, remember? Every time we press, let's go back to our Visual Studio. We are in an infinite loop. We're just picking points, and every time we do pick one, we just add it to the document and add it to our array and set the command resolution to success. So we are doing this in an infinite loop until we press enter or escape. So we can continue doing this. Now I will press enter and it will tell us that the user drew 8 points successfully. Now you saw, let's delete this and execute the command again. You see that every time I pick, we get this, the user drew 1 point successfully. Why is that the case? Let's check quickly. So the reason why this line is written after every point pick is because it's inside this while, the infinite while loop. What we will want to do is get it outside of the loop, and then only once all the picking is done, it will tell you how many points you drew. Now, we don't want to necessarily only pick points. Let's learn how to select points as well. So what we will want to do is we will want to create a new command. Let's speed this up a little bit. I feel I'm going too thoroughly through everything. And let's call this one a point selector, because we're not picking the points, we're actually selecting the points that already exist in the document. What I will do now, I will go up here and immediately start by using a couple of namespaces that I know I will need. Maybe I won't need all of them, but let's use them just in case. My Rhino input, my Rhino input custom. I will want to use Rhino collections because I will probably use some arrays. And what I will want to use is some Rhino geometry, very probably. Let's see. So what I will do here is I will instantiate a new get object class. And before we had get point, which was specialized for points. Now we will use the get object, the one we can use basically to select any type of object. It's much more general and it will be very useful because this is how we will select most of our objects. Now the cool thing about get object is that it comes with a lot of cool methods that can customize the way you're selecting objects. And I will show you a couple of them now, and you will see much more in the following videos. And of course you're free to explore the rest of them on your own if you go to your help file and your get object class and all of these methods that are there. So you can put a geometry filter. Let's see how to do that. We can say our geometry filter will equal Rhino doc objects object type. We will using all these paths just to get to our object type enumeration. You can avoid this by using Rhino doc objects here if you want to. I just need this enumeration, so I have to get to it. And this enumeration can be used to filter the objects. Now, the user will only be able to select the objects of type point. And very importantly, you can actually choose the minimum and the maximum of selected points if you want. We will use the so-called getMultiple method. And you can find this method in your help file. I will put 1 and 0 here. You can find this method in your help file. It's right here, getMultiple. And you can read the description here of the inputs. You will notice that I put 0, and it says here if its maximum number of objects is set to 0, then the user must press enter to finish the selection. So you're kind of entering this infinite loop that we had before, where the user actually has to press enter. And of course, you can have the obligatory check if the result of the picking was a success or not. You can say you can access the command result of your Go object, and if it's not equal to success, then you can get out by returning whatever the command result is returning. If everything is successful, you just want to continue. Let's say that the user actually selected a couple of points, and now we just have to save them. So what we will do is we will create a list of points, and as I promised you before, we used point 3D list. Now I will introduce some variety. I will use a different type of an array. And the type of an array I will use is called list, and the reason I can't access it here is because I need something for the list. I will need a system library, not a system namespace, not a Rhino namespace at the moment. The one that's called collections, generic, and now I will be able to use lists. I will give my list the type of objects that I want. It will just be a simple point object, and I will set the size of the array, and it will be the same size as the object count property is holding for our object. So however many objects or points user selected, that is how big this array will be. And you will see that here my list is underlined. That is because I forgot the new keyword. That's the point. We are creating a new array here. Now what I will do is simply enter a loop, a for loop, that I hope you know how it works at this moment. This loop will go through all objects, and simply we will extract a point from our object using our get object object. I'm sorry for using that word so much, but that's is the problem when you're what you're referring to has the class with the same name. We access the objects we selected, we pass it the iteration, and then we access its point. And if what it's returned is actually a point, everything is okay. So we want to say if the point is not null, this variable is actually holding some reference. Forgot the equal sign here. If it's actually holding some reference, all we need to do is add it to our point array. So let me repeat what I did here. We enter the for loop, and inside for every object that is selected, we can access it through a Go object. We can use the I iterator, and we access the point property, which will return the point that we need. Let's build it and see if it works. Now I want to point something to you. Before we used point 3D, if you remember, to write points, and now I kind of write point here. Why did I do that? Well, if I did write point 3D, we wouldn't be able to add this point to our array. Why? Because for some reason this method will return, as you can see, a point type and not point 3D type. For some reason people at McNeil created different types that can hold a point, and point is a class, and other types like point 3D and point 2D are structures, And if you don't understand the difference between structures and classes, you can check it out online in my videos, but it is not important for now. Structures are just simple versions of classes. And we could be inventive here with different solutions, but I went with the most obvious one. Instead of creating an array of 3D points, I created an array of type point, and everything works fine. You can use this one as well as the point 3D. And what we can do at the end is just simply check out if we did save our array correctly, and we can write the same as before. The user selected this many points successfully. How many points? Again, we will access the count of our array and set it to string. And now you can build and test your command. You can reinstall your plugin. And now as an exercise, you could actually add a button here. And you could put the point picker on the left mouse button click and the point selector on the right mouse button click, just to have it interested. And you remember the difference? In order to actually select points, you need to have them in the document. So what do we have now? We have 7 points, and if we start our point selector command and we actually select all of them, press enter, it will say the user selected 7 points successfully. If we start it again, select nothing, press enter, nothing happens. Why doesn't anything happen? If you remember here, our result will not be success, and we will just get out of the function. We will not even get to here. If I press escape or right button, again nothing happens. It's the same thing. So let's continue. Okay, this video was a bit long because I wanted to be thorough at the beginning. We're going to speed up from here a bit, and if you do not understand something, do not worry. There will be a lot of repetition and you will understand how the selection generally works. And you will learn that for every method there are multiple ways of doing it, and all of those methods can be equally good. It will just depend on your routine and your practice. Now you can do different things with the curves. So let's just, as an experiment, inside this loop of our curves, let's do something. You can access the start point and the end point of the curve. So I will talk about creating geometry, so drawing geometry in the document in the next section, but from time to time we will use it just to make a point, like here. We will access our objects table and we'll add a point. What point? Well, we will add the curve that we're dealing with in this iteration, and we will access the method called point@start. And this is it. This will just return the start point of the curve. We can do the same thing again, copy paste it with the point@end. And we can redraw views. You can choose if you want to redraw them after every iteration here or outside the loop. So now basically if you selected curves, you would draw a point at each curve's start and end. And we will see that, but let's add something else. Let's read the length, for example, of each curve that is being tested, and let's write it down. So this we will write inside our loop for each curve. So let's say we have some string that's called curve info, and we will format it like this. We will say the length of the curve is this. And we can access the curve length with a simple method called getLength. Of course, this is a double precision number, so we will want to convert it to a string. And if you want, you can use that formatting that we used before. If you remember, was it here in our Variegola comment? Exactly. If we don't use this type of formatting, we will just get like 10 decimal places. But if you want, simply copy this line. Let me do it for you. Copy this line here. And now we will have the display precision defined in the document, which is usually 2 or 3 decimal places. And what you need to do is just pass this format as an argument. As I said, This is not necessary, you do not have to pass anything here, but it will just print the length with like 10 decimal places. Now you can test the command, see if it works, and then we can add some more, couple of other things to it. It's pretty easy, you just have to explore all the methods that come with curve in your SDK help file. I will draw 3 freeform curves, and I will start my curve selector, and it says that the user selected 0 lines, 0 polylines, and so on, because we only have freeform curves, and we added our point to the start and to the beginning of every curve. Why didn't it actually print the length of the curves? Because we just, again, did the same mistake as I did before, I think. We defined the string, but we did not actually print the line. So we actually need to print the line to see the lengths of the curves. So now if I start my curve selector and select them, you will see I will see the length of each curves in the order of selection. And I will talk about that a bit later as well, but if you select a lot of objects at the same time, then the order of their selection will be the order in which they are drawn. If you select them one by one, so let me start the command again. If I select them one by one, first this, then this, then this, then that will be the order. That will be the order of the array. You will see it's a bit different here. But you will learn that as you go along. So every curve as well as a surface has a domain. That's one of the main characteristics of the NURBS geometry. And I explained all of this in different videos and in my NURBS classes. You have to check if they're out yet. If they are, there will be links posted. I'm not going to explain now what the domain is, but I will show you how to read it. So if you go to your help file, you will see that there is in your curve class that there is a property called domain, and you can read a little bit about it, explore it. It's not such a big deal. I will show you how to use it in code. We can format our string differently now. We're not going to only explore the length of the curve. We can say the curve 0 has the length 1. This is what we will hold the length, and domain from this value to this value. Now we will simply have to provide all of these things. So the curve, the name of the curve will be just the iteration, not is, but an I, because we are iterating here, remember, in the for loop. So this will say the curve 0, the curve 1, the curve 2, and so on for all curves that you selected. Then we will get our curve length and transform it into a string. This will go here. Now what we will want to have is our domain, and this is how we will access it. We will access the property, and the start domain is just the marked as T0, and we will put it to string using our formatting, and the end domain of the curve will be T1. Again, if you do not understand what a domain is, explore it a bit. It's very important part of the NURBS geometry. We will need a comma here. 0, 1. This comma is too much. Okay, let's test this. See how it works. So again, we can select some 3 random curves that I will draw right now. We'll use our X. Let me select the third one. Draw the third one. X curve selector. I will select them, and I will get for every curve. The curve 0 has the length and the domain 0 to something. Now, I don't want you to confuse you a lot, but I do want to confuse you a little bit. These numbers that you're getting from domain, they do not have much sense for you. These curves are represented as mathematical formulas, and the domain might seem random. Sometimes it actually might be very close or the same as the length. And it doesn't have to start from 0, it can be negative, etc. But you can actually easily reparameterize a curve, set your own domain, and you can do it like this. Very, very often you will want to use domain to divide the curve, to do different parametric operations, as well as with surfaces, as you will see. So sometimes you will want to reparameterize it, and you can do it simply like this. You can take your domain of your current curve and you can give it a new interval from 0 to 1. Now if you tested the command again, every curve would have a domain from 0 to 1. And if I want to draw a point exactly at the domain 0.75, which means 3/4 of a curve measured from the start, we can do that. So I will show you right away. We changed our domain. We drew a 1 point at the start, 1 point at the end. And why don't we draw 1 point always at the 3/4 of the curve measuring from the start? So we will call a method called pointAt, and this method will want a domain. And because we know that our domain is now from 0 to 1, we pass 0.75. If we didn't do this reparameterization, what we could have passed here was simply curve domain divided by 4 times 3, and that would kind of be the same thing. It would be 3/4 of a domain. But sometimes it's easier to work with a clear interval that is always from 0 to 1 and disregard the actual numbers. So both options are acceptable. I'm just trying to show you that you have different options. We start our curve selector, select them, and now as you can see we have a start point, an end point to every curve, and a point added every time to the 0.75 domain of the curve. And as you can see here, all the domains are 0 to 1 now. So you can experiment with that, play with that, and let's go on and see what we can do with surfaces. As I said, there are many different types of curves and lines, and you can explore them on your own, and I will explore them as well in higher level courses. But the important point is that they can all be selected using the curve abstract class and then handled on later. And then we will see how. Just to clarify a bit for you, a polyline is represented through an array of points. So it's just a different version of a point array. If you find the polyline in the SDK help, you will see that it is inherited from a point 3D list. But since there is a polyline curve as well, we can talk about it as a curve. Now this might be a bit confusing for you. I know it was for me. Why is there a line and a line curve? Why is there a polyline and a polyline curve? You will find out what the difference between a line and a curve is at the end of this section, but the simplest explanation is that line is much simpler and curve will have all the NURBS properties, as I mentioned, control points, knots, degrees, domains, etc. Now let's move on to selecting surfaces. So you learned how to pick and select a single point or select multiple points and save them in an array, and how to use that information. For now we just read their coordinates and the number of points in the array, but in the future we will be able to use them in many different ways. Let's now go on to curves and try to select some of them and see what we can get from them. Okay, so let's make a new command. Let's call it, follow our new convention, call it curve selector. It's a CS file. And why don't you just go and simply copy some of the namespaces just to be sure, just not to go through that again unnecessarily. So we can start the same way as we did with the points. We will define our object, let's call it GC now for getCurve, but it will be also an object of the getObject class. We can set the command prompt to select some curves. That makes sense. Then we will want to select our geometry filter. For that, we will want to access the object type curve. And if you remember last time, this is how I accessed this enumeration with Rhino doc objects. Why don't we just add this entire namespace here. And now we can simply type object type enumeration, and I want curve. So the user can only select curves now. We can test it. You can test this later and see if you have points or surfaces and the user selects them all at once, the selection will only filter the curves. We will use the get multiple option so that the user actually has to press enter once they're done with the selection. And we can check. Let's just simply go to our previous command and copy this check. Of course, we will have to exchange our object with GC. So if the command result is not success, we just get out of the function. Now what we want to do is create a collection of curves. What I'm not doing, what you should definitely do, I'm not doing it for the speed, you should comment everything that you're doing. So in this case, I will write something here, and we will create an array of curves. Again, as with other arrays, there are multiple options, from simple.NET arrays over lists, over Rhino lists, and the specialized Rhino arrays, but we will go through all of them at some point. I will again use a simple list with the type curve, and again I will initialize it with the object count that we have. I will initialize its size like this. Now, as we did before, we will enter the loop. Let's go to our point selector and let's simply copy this loop and see what will change here. Well, first of all, our object is not GO anymore, now it's GC, but we will go through all of those objects. We don't want a point, we want a curve, so let's call our variable curve. We will access the GC, we will access its objects, and instead of a point, we will get a curve. Makes sense, right? And if our curve is not 0, our curves array will get a new curve. That was fast and neat. So in a couple of minutes you basically have a command that selects curves for you. So let's just copy this line here so that we know if our selection was actually successful, if we added them to our array. Let's say the user selected X amount of curves successfully, and we will need our curves array here. So we'll test it now, and we'll go through different options shortly so I can show to you how you can play with it. We will need our plugin manager to reinstall our command, and if you want, you can add another button here that you will use to select your curves. Now I will show you what I told you before. We will copy this curve 3 times, and we will add some surface in between, and we will add some points. And if I start my curve selector here and I select everything, okay, in this case the edges of the Brep are also curves, but as you can see, my points weren't selected and my surface itself weren't selected. If I press enter, it will say that the user selected 3 curves successfully. So you see that the geometry filter works, you see that our selection command works, and for example, if you limit your selection to 3 and test your command now, you will see that you will be able only to select 3 curves. If you select exactly 3, you will not be even asked to press enter to finish selection. And the same will happen if you select them one by one. You can exercise on your own. What you can exercise again, actually it's not a big exercise, you can just change it here. You can use your curve list class. It's a specialized class that comes with Rhino that holds an array of curves, and this code should work just as well with that one. And I told you that curves come in many forms. Line is the simplest one, for example. There's a polyline, arc, polycurve, etc., etc. And if you want to be sure that you selected a specific type of a curve, there are some functions that might help you with that. So let's go shortly to the help file and see how we can recognize what type of curve is selected. Now if you go to your curve class and in your help file and look at its methods, you will find there is lots of interesting methods. And if you go to the is ones, you can see that there are functions that can actually check for you if the curve is an arc, if it's a circle, if it's a linear, which means that it's basically a straight line, if it's too short, and so on and so on. And by using these methods, you can test it and know what you selected. But there is also kind of an easier way to do that. And I will use this simplified version, simplified form of classification. And you can maybe experiment on your own later with these functions. So let's make our command interesting in the following manner. I will set something like this. I will set an integer values that will hold the numbers of lines that we selected. Then it will call the numbers of arcs, hold the number of circles, and polylines. So what we will want to do is want to see which type of curves did the user select. So we added the curve to our array. That's okay. We can leave that as it is. Now let's check if our curve is a line. And this is the very simple version of that. You can create a new object of type live curve, and then you can write this equals curve as line curve. If the line curve object is not null, if it actually has some value, that means that our curve is actually a line, and we can increase our line count. So why does this work exactly? Well, if you're wondering about the as keyword, that is the simplest form of castings or conversions, and I will not explain them here. You can check it online or in my basic courses, but it's a lightweight option of so-called casting, because if it's successful, it will return exactly what you want. If this is not successful, if this casting of a curve into a line curve type was not successful, this will simply be null. And for our purpose, that is usually enough. But if you want to use some of these methods, like is linear, you can use them as well and try how it works with them. What we can do now is do the exact same thing, only we can do this with the polyline curve, polyline curve, and we can of course call the object polyline curve. I hope you're seeing what I'm doing this. I'm just exchanging. You will have all this code available, so you'll see what's happening. And we will do a little bit more complicated for the arc curve. We will try to cast our curve into an arc curve. And if this cast was successful, then we might want to do an additional check, because you see the circles are just type of arcs, kind of a subtype of arcs. So you can check if our arc curve is a circle, and here you see I will use one of those methods that you saw there. This is how you can use a method is linear or is arc also up here if you want, but I will leave that to exercise. I will leave that exercise to you. So if our arc curve is a circle, we will increase our circle count, and if it's not, it means it's a simple arc. So we will increase our arc count. Now let's read what we did. We will use string formatting for that. I will use some string, and I will say string format. I can say the user selected this amount of lines, this amount of polylines, this amount of circles, this amount of arcs, and this amount of curves in total. So now we will just have to list our integer values, cast them to strings, line count, polyline. You can also put this in the next line if you want to make it more readable. Line count, polyline count, we have our arc count, no, circle count goes first, arc count to string, and of course we want the numbers in total, which will be the count of the curve array to string. And of course, after every toString, I forgot the brackets here because it's a method, not a property. Of course, what you will want to do is actually write this string somewhere. Write line, and we'll just put our string here. Now, before we test our command, you will very often make mistakes in typing, and as you will see, I made a mistake here. I increased the line count for polyline curves. I will need to increase the polyline count, do not forget that. And what I want to do is not print the results in every iteration of the loop. What I want to print is at the end of the loop, and we don't need this, the user select curves successfully, because we will kind of print how many curves we selected here in total. So let's build this and test this command. Let's prepare something for selection. Let's create 2 circles. Let's create some arcs. Let's say 3 arcs. Let's create some straight lines. Let's say 4 or 5 straight lines. Let's create some polylines. Here is one, here is one, another. And let's create some free-form curves, just to have everything. And now if you start your curve selector command and select everything, you will see it says the user selected 5 lines, 2 polylines, 2 circles, 3 arcs, and 14 curves in total. So our command worked. We did recognize different types of curves. So let's go to the next video and see what else we can do and what else there is to read once we select the curves. We have learned how to select points and how to select curves, and that curves can have many different shapes. And we learned how to transform them or cast them, to use a programming expression, into different forms. We can use them in different ways. I will cover some of the different types of curves and lines, but not all of them, because there are many of them, and the logic is the same, so you can easily do it yourself. I will also cover some more complex one in the higher levels of the course. Now let's go to heavyweight objects now, like surfaces and polysurfaces. As I mentioned before, if I already made a course on NURB surfaces, you will find the link in the description. If not, there will be at least some links to some of my videos where I discuss NURBS geometry. So assuming that you know what NURBS geometry is, in Rhino you can model with surfaces, and if you join them you can create polysurfaces. Then you can trim them, split them, modify them, and all that information has to be saved. That is why we have a class called Brep. And when you create an object of this class and you save some surface or polysurface you created, you will have all that information packed there. A nice explanation of Brep structure can be found here if you follow this link. And although this was made for C++, you can ignore the variables and concentrate on the constituting parts. As you can see, there are all these different types of data stored inside a Brep structure, but I will not go through it now. We will address it in some of the higher level courses. For now, it's enough acknowledging that Brep is a very powerful and complex class, and it will be a source of a lot of joy and a lot of headaches. Let's select some Breps now. Let's create a Brep selector in the way we already learned how to do. A new item, a command called Brep selector. Let's go to our curve selector and just copy all the namespaces that we used. And what we can do is definitely copy the first part until we actually come to the array. Let's copy this part first. This is what we will do very often. You will copy and reuse code and you will change it. And what I will do is I will not change this to GP now, like get breps or something. I will leave it to GC so we can use the same syntax. We will select some breps instead of some curves. Our geometry filter has to be object type brep, because that is what we want. We want surfaces and polysurfaces. We will get multiple breps. We will check if the command is there. And what I will do now is I will use a new type of a list, new type of array, just so we can go through most of them. And it's called Rhino list. It's basically the same as list, only Rhino inherited from it and added some methods that are convenient. We will have a Rhino list brep called breps. We will create a new one. And we will not tell it exactly how many elements will be in array, because we will dynamically expand it. So we will enter our loop for all the objects. That the user selected, and in a very similar way we did before, we will simply create and test if we get something when we call the brep method. If we do get something, it's not, what we got is not null, not an empty memory, that means we can add this brep to our array. And again, in very few minutes, we basically forgot to pass I here. It's very important. And we basically have our array of breps. And what we can do, again, like we did in our curve selector, if you want to, you can put a little line here that says that the user select this many breps successfully. So I went fast through it because there is nothing new here. It was all a copy paste. So let's address the pre-select here, because it can be important. That means if you select some objects and then start the command and pre-select is true, it's enabled, then those objects will come into consideration. If you don't enable the pre-select objects, and this is how you do it, you basically just pass false here to pre-select, then everything that is selected in Rhino will be disregarded, everything will be deselected, and selection will start from 0. Except you also need a second argument in this new version of the method, and you can check out what it is. Although it's pretty intuitive, it's as it says, it will ignore unacceptable pre-selected objects. What you can do now is you can test this command if you want. I will jump shortly just to see if it works, not show the whole process. I reinstalled the plugin. I drew some surface with 4 points. I can actually draw a box. A box is a polysurface, which is actually also a brep. So if I start my brep selector here and I select all these 3, it will say the user selected 3 breps successfully. So the brep selector in its own works. Now let's see what we can actually get from a brep. As I mentioned in this section, we are not creating objects, we are dealing with selecting and reading from them, which will usually be a large part of your methods. So let's see a set of things that we can read for a brep object. As I told you, brep can be a surface or a polysurface. So how many faces does a brep have? This will tell us if the brep is a single surface or a polysurface. So let's add that and test it. And remember that we will do that formatting only to set the display precision. So I find it pretty useful. So I can always copy it here. And we can set our string. Notice that sometimes I'll use string, sometimes I'll use var. It's very convenient in .NET that you can use this var and it will be determined on its own. I will format a string to say following. Brep the current Brep in this iteration that we are. So if what I want to do is actually get inside the iteration, get inside the for loop. So the current Brep 0 has this many faces. And how will I know that? First I will put the iteration of the Brep, and I can put that to string. Before I didn't do it, but it worked anyway, so for some in some cases you can actually avoid it, but it's a nice habit to have. And then what we will do, we will access the faces property of our Brep, and then we will simply access their count, which, I'm sorry, is not a method, it's a property, so this is how you will access it. And of course you want to write this down. So let's start with this. Let's analyze this with a little bit of help file. So we can go to our Rhino geometry, and we can find our Brep class, and we can find our Brep properties, and we can see their faces. So what are faces? It's just a Brep face list, a specialized array that holds faces. Type is a Brep face list, and as we can see, it's just a list of Brep faces. You can then go deep digger, you can go to your Rhino geometry and then find what a Brep face is. Here is a Brep face class. That means that we can access each of the Brep faces of a polysurface separately by accessing this Brep face, and you can see that Brep face is basically a surface proxy. It's inherited from a surface class. So that kind of gives you an insight a little bit about the Brep structure that is created out of multiple surfaces. You can even go further and press the surface and examine it, and the surface has some properties that we can read. So for example, we can for example read the area that our polysurface has, and then read the areas of the single surfaces, and we can do this in the following manner. Let me show you. We can say here how many faces we have. I make spelling mistakes constantly, sorry for that. And we can say, and the total surface of, I'll put something here. Now I will put the surface here. And I will use the Brep and its getArea method, which will give me the actual surface of the entire Brep. And I will convert that to string and format it. Now this will show me the surface in some units, whatever the unit is of the Rhino. But if you want to be meticulous and actually write, you can say the total surface of this much square centimeters of square meters. So you can actually say square and retrieve the unit from the document. This is how we will do it. We will add another variable here, which we will for which we will access the document, access the model, unit, system, and show that as a string. So before we continue, let's test how this works, how we read the number of faces in our Brep, and then read the area of the entire Brep, and then actually read the model units from our document. So I told you that a box is a simple polysurface with 6 edges basically, and next to it we can create one very simple surface. And if we use our Brep selector now and select these two objects, you will see the first one, which is our box, Brep 0, has 6 faces and the total surface of this much square meters. You see, this was read from the document and shown here. And you see that our second Brep has only one face and a certain total surface. Very well, we can read those things. So now let's deal with each face individually, so you can learn how to access each face individually. And if you check the help file, like we did, you can see that the Brep face or surface do not have a getArea function. So what we have to do here is use area mass properties. And here you will learn how to use that as well. So what we will do now is we will come here and we will create a second loop through all the faces of a certain Brep. And as you can see, I always kind of instantiated I here right before I enter the loop. What I can do now is go up here all the way up to our command and make two integers, I and j, that we will use. And now we can use them freely here. And I can use my j for my second nested loop, where I will go through all the Brep faces. For that, we enter the faces and the count. And then for each face, I will do something. So what can we do? We can read the area of the face. Area is saved in the area mass properties class. Let's call it Brep face mass. And we will call the static method of area mass properties class that will compute the area of the Brep face that we pass, and we will pass the current iteration, our j. So at this moment we are holding the area of the current face that's examined of this Brep. And now you will want the number, the actual double precision number of the area. Call it Brep face area, and you will use this object and access its area property, and that's it. This will hold the number of square meters or centimeters or whatever the unit is of your face. And now we can write all of that down. I will just speed up through the writing so that I don't waste your time, and you can pause your video and look at this here and rewrite it if you want. But what's happening here is we just wrote the Brep face j iterator belonging to the Brep I iterator, so the higher loop, has the surface of this many square meters. So we're doing kind of the same thing as we did here, only now for every face. And you will notice that the order of Brep faces is not the one that makes sense to you, but the order in which they were drawn or changed. So if you want to know exactly which surface is what, you will have to mark them somehow. But do not worry, we will go through different types of annotations so that you can use something like that if you want. And just to make it a little bit more complicated, in the same way that curves have a domain, surfaces have a domain as well. Of course, in 2 dimensions. Actually, if you draw a curve in Rhino and write domain, you can see what it is. And the same works for surfaces. Notice that I'm saying surfaces and not breps, because polysurfaces do not have a singular domain. Only its building blocks, the underlying surfaces, have domains. And domains are very useful if you want to divide a curve or a surface into equal parts, or if you want to draw over them. A domain helps you define a parametric space. You can basically draw in 2D, act as if the surface is a piece of paper with x and y coordinates, except that in NURBS world we use u and v to describe the 2 directions. I will explain all of this in much more detail in the NURBS lessons. As I told you, in Rhino you can use the command domain to give you the domain of the surface. So let's extract this in our code as well, so that we know how to use it later. In the same way as we did it for curve, except we will have to tell the function in which direction. So you can pause the video if you want right now and write this. I sped it up just so that you do not watch me type this, and I will explain what's happening here. What's happening here is that we are continuing this string, as I will show you right away here. We're writing some Brep info here, but we will want to write Brep face info here, and it will have 2 strings. It will have Brep face info plus Brep face domain. So we will write Brep face belonging to Brep blah blah blah, and then we will continue here. And its domain is u from 0 to 1 and v from 2 to 3. So we will access its faces and its domain, and this 0 that we passed says we are dealing with the domain u in u direction. And again, as with the curve, we can access the start of that domain, t0, and the end of that domain. And that happens with the v direction as well. We access the v direction by passing 1, and then the start of the v domain direction and the end of the v domain direction. So if you start this command, it will write a hell of a lot of things. but it will be good to know. And as an experiment, what I want you to do is create one box. Then I will want you to create one plane surface, just to see what happens with a single surface. And then I want you to copy this surface like this 3 times and then join this. By joining them, you created a polysurface. So these two are polysurfaces and this is a surface. So what happens if I press my Brep selector and select them all? You will see that now for each face of these polysurfaces I will get something like this. Brep face 0 belonging to Brep 0. So all these 6 lines refer to this box, apparently, because there are 6 faces. It will tell me the square meters of each surface, of each face, and it will tell me the domain of each face in U and V direction. So in U from 0 to 10, in V from 0 to 7. Then it will go to this simple surface here, Brep face 0 belonging to Brep 1, just one face, and then as you see it will go to my new joined polysurface and do the same thing. As then you can see all 3 faces are the same, they have the same square meters and the same domain. You can explore this, test it on a bit. I know it's a little bit too much information, maybe rewatch this video, but these are some very useful information. And using this template you can learn how not only to get access to the area of the Brep or the area of the Brep face or the domain of the Brep faces, but many other things that you can find in the help file if you go and check the Brep face and check the Brep methods itself. I think we deserve a rest from Breps a bit. We need some time for all this to sink in. So let's move to meshes. They are very simple in comparison to Breps. We covered selecting points, curves and surfaces and polysurfaces. I mentioned that there are many other types of objects in Rhino, like annotation objects, for example, text dots, dimensions. In this level 1 course we will mention some of them, create some of them, and leave the more complex operations for higher level courses. But we still have to cover one more important geometry type, the mesh. Mesh is the geometry type when we are talking about computer graphics. As I mentioned many times before, if you watched Pirates of the Caribbean or The Avengers, all those CGI objects are meshes, collections of triangles and quadrangles. Even the NURBS geometry you create in Rhino is transformed into a mesh in the background so that it can be rendered. If you go to Tools, Options, Mesh, for example, you can adjust the density of that render mesh, the viewing mesh. So if you choose the second option, the preview mesh will be finer, but the render time in your viewport will be slower. Rhino is created for NURBS modeling, so you will not work with meshes as much as in other software like AutoCAD, Revit, or maybe 3D Studio Max, Maya, etc. But sometimes you will. Let's simply go into our Rhino and create some simple surface or polysurface and use mesh command to transform it into a mesh. So you can do this. I can make a simple plane surface, then I can rebuild it to 5 points on each side. That's okay. Turn on the control points, move some points vertically, and what I can do now is use the mesh command, which we will learn how to use in the code. I can see the preview. That's okay. I can go to simple controls, make it more detailed, less detailed. This is okay, and I created a mesh. I can actually delete my surface now, and I'm left with a mesh. What you will see, you have also mesh sphere that you can draw as a command. What you can see, you can have a mesh box that you can draw, and it's all nice and neat. And you can save this file. Let me save this file because we will use it right away in our code. I will close Rhino, and we want to create a simple mesh selector. Do not forget the X at the beginning so we can recognize our command. And in the same way we did it before, let's just copy paste the things from our previous commands. We will Of course, do not forget to copy and paste all these namespaces that we will need to use. We will select some meshes. As we can see here, our object type will be mesh, our object type filter. We will disable pre-select, we will get multiple objects, check if the command is valid or not. And we will again use the Rhino list, except we will use the mesh type for the list. We will call our array meshes. And we will enter a loop like we did here. I will copy the top part of the loop and just not forget to close the curly bracket here. And we will check the mesh from the mesh method. And if everything is okay, we will exchange all these words that are brep with mesh, meshes. I hope you're realizing what I'm doing, and I hope you're doing it as quickly. If not, you can simply pause the video, check the code, but you can also examine the code that you already have, that I provided you. And at the end, as we always did so far, we can simply write how many meshes our user successfully selected. So if you tested this command, it's nothing new, it's what we already repeated for curves and for breps and even for points. Your user will be able to select the meshes, and we will just write down how many meshes we saved in our array. So let's talk about meshes. In the video where I talked about different geometry types, I told you a little bit about it. I'll also recommend for you to see this video where I talk about differences between mesh and NURBS geometry. Now, a mesh has faces that are triangles and quadrangles, and a mesh has vertices and edges, and all the operations you will do with meshes will involve faces and vertices. It's very important to know how to access them. So the first step is seeing how many of them are there. So let's do that. So for our mesh, inside of our loop, because what we do in these examples is we always select multiple objects and then we go through all of them and do something, just to show you that you can do the same thing for different types of objects. So again, nothing new here, very intuitive. We can save the number of faces, the face count, by accessing the mesh faces in the similar way with as with breps, except that mesh faces are not surfaces, they are very, very simple structures that only have 3 or 4 points basically. So we will access the count of faces, and let's call it vertex count. We will access the mesh vertices and see how many of them are there. And you can simply write, as we did before, mesh info is a string format, mesh particular current mesh has this many faces and this many vertices. You will write the iteration, put it to string if you want to. You will write your face count also as a string, and you can write your vertex count also as a string. You will not want to forget to actually write the line before you test it. And you can test it on your own quickly. The best way is to open the mesh file that we saved already. As I did before, you will use the plugin manager to reinstall your plugin, because you have a new command, and then when you simply execute your X mesh selector and you select your meshes, you will be able to see for each one of them how many faces and vertices they have. Again, if you turn on the control point, you can actually select and see that this one has 92 mesh points or 92 vertices, as we can see here. So, good. What can we do now? The interesting thing is that you can actually change the vertices. So what will happen if we actually do this? What if I go into another loop, a nested loop here, and go through all the vertices of my current mesh. And then for each vertex I will create my own new point. Let's call it new vertex. And this point will hold the current vertex that I'm iterating through using my J iterator. And what I will do now is I will access this new vertex of mine, access its set coordinate and set it to 0. What I'm basically doing is reading the vertex and projecting it to the base plane. What I can do now is access again the vertex, the vertices array of my mesh, and I can use the set vertex command in order to change a specific vertex. So I will pass the J iterator so that the method knows which exactly vertex to change, and I will pass the value of my 3D point as the new coordinates of this vertex. Except, of course, this is a normal method. I'm not going to use the angle brackets, I'm going to use the normal brackets. After this is done, this loop of vertices, I will actually want to access the object table and add a mesh. And which mesh I will add? I will add this same mesh that we just changed here in a loop. And I will shortly redraw. So I hope you understand what's happening here, and I hope you can guess what will happen once I start the command. If you didn't guess it, here is what it will happen, and for the demonstration I will move these meshes. So now if I start my command and select this mesh, what happens is that as you saw, we iterate, we go through every single vertex on this mesh, and we set its set coordinate to 0, we basically project it to the ground, and this mesh will become this one, and we draw it again. I know that in this section we read geometry and not create geometry, we do that in the next one, but I just want to show you that meshes are pretty cool and there is a lot you can do with them, and you can explore all this yourself, and my hope is that all the time I'm investing in slowly explaining the fundamentals to you will pay off, because you will understand the principles and be able to intuitively develop more complex forms of the code we are developing here. All you need to know is that something exists. If you know that or assume that, you can easily find it later in the help file and apply it. For example, you should know that every vertex of the mesh has a normal vector calculated from its neighboring faces and vertices. So let's access that normal and draw a simple line out of it. The normals property will return a mesh vertex normal, and you can check in the help file. You will see that the normal property of the mesh vertex normal is a simple vector. If you go and find the mesh vertex normal list, you will see that it's just a collection of vector 3f, and there are 3f and 3d points and 3f and 3d vectors. The only difference is the float, or single or double precision of the coordinates. The difference is very subtle and for our purposes not important at all. It's just you need to know that these f are less precise numbers than the d ones. You can just acknowledge that here, and that there are different types, and that if you want to explicitly name your variable, you sometimes have to pay attention to what the method is actually returning. So we can comment out the part where we actually flatten our mesh. We do not want to flatten it anymore. You can comment this out. You can use the tab to push it a bit on the side. Actually, what I want to comment out is the drawing, the redrawing of the mesh as well. You can push everything on the side. And now notice that the number of vertices and normals should be the same. Of course, there is a normal for every vertex. And before we proceed with playing with normals, we can actually check that if you want. You will want to do these checks all the times, just to be sure that everything works well. So you can say if the normals count not equal vertex count, then I will continue. What does this mean? Continue. I urge you to check online or in my C# basic lessons where I explain for loops. It just means that we will skip whatever comes after this underneath, and we will go back to the next iteration of the loop. So when we can create a simple line there then at every vertex following its normals. So let's see how to do that. We will enter another loop as we did before. Actually, we can copy this code here because we are entering a loop for all the vertices. And what we will do, we will save the normal vector by accessing the mesh normals and the particular normal for this particular vertex. And what we can do is we can create a simple line that starts from the vertices, from the vertex at the j iterator, and then ends using the same vertex, but now adding the normal vector to it. We're doing it with basic geometry. We create the line with 2 points, and our second point is simply a sum of the vertex point and the normal vector. The size of the normal vector is 1, so 1 unit, whatever unit you are working with. So if it's meters, it will be 1 meter. How do I know it will be 1? The normals that are usually returned like this, the vectors that you can access with Rhino methods, never mind the spelling mistakes. The Rhino methods usually return unitized vectors, which means giving the vector with a value of 1. When you deal with vectors that you create on your own, you should always use the unitize function for the vector. Then you can multiply it by any value and you can get an exact length. So what you will want to do now is go to your doc objects and actually add this line to the document. I will call it normal line here, just so that we have some sense. And at the end, if I want to, I can, of course, use my redraw. Now, if you understand what happened here, then you will understand exactly how the execution of this command will go. I will start our mesh selector, select our meshes, and as you will see, from each of our vertices, we will get our normal vector, and we will use it to create the line. Now, as I told you, you can multiply the value of this normal vector with some number, and you will see that the length of the line will change. And we can do an interesting thing. We can actually ask the user, after they select the mesh, and before we get into this loop, we can simply put a block here where we ask the user to select, to give you, or to input the length of the normal vector. Something also that's useful. Let's see quickly how to do that. We will create a new object of the class getNumber. So following the same basic principles, we will set the command prompt. We will say, tell me the length of the normals. And then we will use the get method to actually get them, and we will save the number. Let's say call it normal mult, as for normal multiplier, and we will retrieve our number. So this is it. After we have selected the meshes here, the user will be prompted again to tell you the length of the normals. So what you should do now in theory is just go to this normal vector, put it in the bracket, and multiply it with this normal mult variable that you get. Now, I have to admit, for some reason here it doesn't allow me to actually multiply a vector 3f with a double. So let me see what the problem is there. You can explore on your own. Maybe we have to cast it into a float number like this. And yes, it looks like it will work. It's a problem because the problem arises because we have a vector 3f, as I told you. It's a float precision number, and it doesn't want to multiply it with a double. And you can actually do a simple casting by doing this. I could have written integer here as well. And now, if I test my command and I start my mesh selector, I will select the meshes, then I will be prompted to tell the Rhino the length of the normals. We had 1 before, let's use 3.5. And now all the lines that are created, you can select one of them, type the length, you will see they're all 3.5 meters long. When you program, you can often deal with single variables, single storage of data. But more often than that, you will deal with collections of data, groups of variables. In the programming terminology, they're usually referred to as arrays, and in .NET framework, you will usually refer to them as lists. Now I talk about arrays and lists in my C# basics lesson, and I will not repeat all of that here. Let's talk about concrete usage in our examples. There are many different ways of making an array or a list. If you know the number of elements your array will have, you could simply write this. By using the square brackets, you can create an array of 5 integer elements. The size of this array is fixed, but you did not define the elements, so you could do it like this, for example. And now you defined all elements, and if you wanted to access the third element, you could say this. Now if I printed the value of the third element variable, it would be 46. Why did I put 2 if I wanted the third element? If you're asking this, you should go to my C# basics lessons and watch the video on arrays again. But in programming, they're always 0 based. That means the first element has always the position 0, the second element the position 1, and so on. Sometimes this leads to confusions, but you will get used to it. When we program for Rhino in C#, we will use some more convenient ways of storing arrays. We will use lists. In the examples in this section, we already use different lists, and some of the syntax that you have seen looks like this. There's another class you can use called Rhino list. This is basically the same class as list, but it exposes a few more methods. You use the lesser and greater symbols to define the type or the class of the element of which you want to make a list. Also, once you start creating your own classes, your own types of objects, you can make lists in the same way. And I showed you before, for some geometry types you have specialized arrays that you can use. For example, we saw that when we selected curves, we used the curve list, and there is also point 3D list. So you can use them in the same way you use a normal list, except that you do not have to specify the type. They're made for storing only points or curves. Once you created your array, like you did in all those examples we did, what can you do with it? Well, I will show you a couple of very useful functions, but as with everything else, you can just simply go to your Rhino SDK help and check out what they can do. So if we just go to one of our examples, let's say our curve selector, where we select curves, you can see that we use the specified array. That's a Rhino class. And you saw before that most useful function in an array is add. As you saw here, we were adding curves to our curve list. This seems simply straightforward and intuitive, but it expands the array dynamically. So this is programmatically actually not a trivial thing at all. Every time a new memory has to be reserved, the capacity of the array has to be adjusted, and so on. So be very thankful for the existence of lists. If for some reason you want to initialize your array with a certain capacity, you can also do that like this. I will just simply write the code here and then delete it, but you can reuse it in your code in any way you want. So imagine you want to have an array that has, let's say, array count that has 10 elements. What you would do is you would define an array or list. I apologize for using array and list interchangeably because they're kind of the same thing. It's just that the lists are more common in the .NET environment, and array is probably much more used in the C++ environment. So I want to create my list, and I will create a new one. I can choose any type that I want, let's say in this case curves, and I can simply instantiate it with, as you can see, if you press your arrow down, you have 3 constructor overloads. One is empty, one has the capacity as an input, and one has some collection. We will use this one as a capacity, and we will just simply put our count. In this way, the list will not have to do resizing when you do add elements, so it will theoretically work a little bit faster. So there's a difference between capacity and count for array, but that is not something you need to think about at this moment. It's a relatively complex for this stage of the learning process and not relevant. So just remember that you can set an array of the specific capacity, which is this, but you do not have to. And most of the time you will not know the size of the array. You will do it just like we did here and then simply add elements to it dynamically. We can also see how many elements we have in an array, which we already did at some point when we access the count property of a list, and it tells us exactly how many elements are there. What else can we do? Well, for example, we can use clear. So let's delete this for now. I just wanted to show you. This is also a valid list, and this curves is a valid array that we are dealing here with. So let's go to the end and just check some of the methods using the dot operator that we can access. For example, there is the clear method. Clear will delete everything in the array, and this variable will be then empty. You can start filling it up again, which is useful in some loops where you have to clear the entire array and then fill it up again. You can use remove, and the description of all these methods, of course, you can find in the help file. And this will, for example, remove the last element of the array, and if I type in remove at, I can put actually the index of the element in the array that I want to remove, and everything else will be adjusted. All elements after it will be just moved one place to the left. Now, some of the functions are very intuitive. You can use insert to insert an element into the specific place if you want. You can see there is an overload with an index and even with a specific type of element if you need it. You can use the reverse, also useful. To reverse the order of the elements and so on. You can explore them on your own, and in our lessons we will use many of them, so you will get familiar with them. For example, there are multiple sorting methods that you could use to sort your list, but they're usually very case specific and not relevant to the basic programming training, so I will leave that exploration to you. And a specialized array like the curve list that we used here, or the point 3D list that we used before, are inherited from the Rhino list. So they have all those functionality as well. Rhino list is just inherited from the list, except that these kind of arrays or lists have some additional methods that are very useful for this exact type of geometry that you're dealing with. Let me just show you and create a point 3D list. Call it L. And now I can access a method called, for example, set all x or set all y or set all z, which would set all z, y or x values of this array to a single value. That's a specific method only built in this one, and you will not find it, of course, in a normal list or a Rhino list. So that was the very basic thing you need to know about arrays. What we did in this section is we touched upon rudimentary things that you need to know about selecting objects. As I said before, in large majority of the cases, your plugin will select some geometry, read some data, and end up creating some geometry. So now that you know the basics of how to select different stuff, in the next section we'll talk about how to create geometry in Rhino. This is the most interesting part. Once you start drawing those points and curves and surfaces and meshes with few simple lines of code, you will feel like an actual wizard, and you will immediately start getting millions of ideas of what you could do. So without further ado, let us learn the most exciting part of programming in architecture and design: create something out of nothing.